Okay, here's another problem in section 8.1 that is an application problem. If you look at the WebAssign for section 8.1, you will see that this problem is very similar to the last problem in that section. Go ahead and pause the video here for a second just so you can read the problem, try to figure out what's going on before I get started. Okay, here's the key to this problem. If a 2-pound blend is equal parts red, green, and yellow, then each color will be how much? Each color will be 2/3 of a pound. And that fact right there is going to help us set up each equation in this system. We're going to set up an equation for red. We're going to set up an equation for green. And we're going to set up an equation for yellow. Remember, I have 3 different batches. Each of those batches contains a different percentage of red, green, and yellow. I have to find the combination of those 3 batches that will give me equal parts red, green, and yellow. Here are the 3 equations for each for this system. The red color is 40% from batch X, 30% from batch Y, and 35% from batch Z, and that's those color percentages you see right here. So that's how those are the numbers, those are the coefficients on each batch that gives me this relationship. If you take a look at these 3 equations, you should see a little bit of a problem. Those 2 equations are exactly the same. So that's going to be a problem. That's going to give us an underdetermined system. Okay, so both equations are the same here. Our first and third equation are the same, so we are underdetermined. Since this system is underdetermined, we have a free variable. Since we have a free variable, we need to parameterize it, and we're going to do that with the variable z, and I'm going to write that out for you now. Okay, folks, you probably noticed a change in the screen format, and that's because I had to resize this problem to fit it all on the screen. So I mentioned just a second ago, this system is underdetermined, so we have a free variable. Since we have a free variable, we need to parameterize it, and we're going to do that by letting z equal t. The next thing I'm going to do is I'm going to set up the matrix for this system. You're going to notice a couple things. First, I'm going to change everything from decimals to fractions, and that's because in my original equations I have a mix of decimals and fractions. I want exact answers, so I'm going to switch to fractions. I'm also not going to simplify those fractions until the very end of the problem. For example, right here, 0.4, I'm going to write that as 4/10 rather than 2/5, and that's just a choice that I chose when I worked this problem out. And then I'm going to go ahead and simplify everything at the end. The other thing you're going to notice is that my matrix is only going to have 2 rows in it. Remember, the third row here is exactly the same as the first row. So it doesn't do me any good to put that in my matrix because it's just going to cancel out in the end. That's why we defined a parameter z equals t. So the next thing I'm going to do is write out the matrix, and we'll figure out how to solve it from there. Here's my starting matrix, and you notice that I did convert everything to a fraction. I haven't simplified any of those yet. In order to get a 1 in the upper left position of my matrix, I need to multiply row 1 by 10/4. That's what I'm going to do now. Here's the second iteration of my matrix. You'll notice that I have a 1 in the upper left-hand corner, which is good, and I have a 2/10 in the first position of row 2. One of the things you might be thinking is, one of the things we've tried to do when we've got these matrices to a position where we can solve them is we try to get a 1 in that diagonal position. Well, we don't have a third row, so we're not going to be able to get a 1 in that third row. But remember, we parameterized z up here, so that third row we don't need because we already know that we're letting z equal t. The next thing I'm going to do is solve for that to get a 1 in the first position of the second row, so that I'm going to cancel out that 2/10 so that I have a 0 in that first position of the second row. In order to do that, I'm going to multiply row 1 by negative 2/10 and then add that to row 2. Okay, so here's the third iteration of my matrix, and one thing I noticed that I want to mention is earlier I said I wasn't going to be simplifying fractions till the end. That's not necessarily the case. In the background, I'm using my calculator to do all the multiplication and addition on these rows, and the calculator is simplifying those fractions for me, so I didn't want you to be confused by that. The next thing I need to do is get a 1 in the second position of the second row. In order to do that, I'm going to just multiply that row by 4. So 4 times row 3 will get me a 1 in that position. I'll do that for you now. Here's the fourth and final iteration of our matrix. We have leading positions, leading coefficients of 1 in each row to get that diagonal of 1s that we've talked about. What I'm going to do now is I'm going to write out the equations that we get from this matrix and then talk about how to solve them. So that first row is going to give us x plus 3/4 y plus 7/8 z equals 5/3. And that second row is going to give us y plus 1/2 z equals 4/3. We're now going to use that parameter of z equals t to solve for y first, and then we're going to solve for x after that. Let's start here with y. Solving for y is going to give me 4/3 minus t over 2. And some of you might be wondering, where in the world did t over 2 come from? Well, remember that z equals t. That's a parameter we set earlier in the problem. And when I solve this equation for y, I get 4/3 minus 1/2 z, or t over 2. Next thing I'm going to do is solve for x. This is going to give me x equals, and I'm going to write this one out in a little bit longer form because there's a little bit more to it. I'm going to have 5/3 minus 3/4 times y, which is 4/3 minus t over 2, minus 7/8 times z, which is t. This all simplifies to the following. X equals 2/3 minus t over 2. And I'm going to let you prove that to yourself by running through the algebra right here. The final thing that we need to do for this problem is write our solution as a comma-separated list. And remember, the solution represents could represent a point in space. This is going to be 2/3 minus t over 2 for x, 4/3 minus t over 2 for y, and then plain old t for z. So if we go back to think about what this means in the context of our problem, in the context of our problem, we have to select a blend of Skittles to get a batch that has equal parts red, green, and yellow. So I have now this parametric solution that says whatever value I pick for z, whatever value I pick for Z, is going to determine what amount I need of the other two blends. Folks, the last thing I'll mention about this problem is that there's one more restriction on T that I just feel obligated, I feel compelled to mention this to you. T can't be 20. And if you think about it, hopefully you'll understand why. The total weight of this blend has to be 2 pounds. So there is another restriction that we have to place on T, and I'm going to tell you what that is. If you're interested in the mathematics behind it, you can ask me in class. But we have to have T less than or equal to 4/3. And that's not, when you do a problem like this in WebAssign, I don't believe they ask you for any restrictions on T. So I'm just mentioning that to you now so that I can feel good about giving you a complete solution to this problem. Again, we can talk about this in class if you have any questions, but I really want you to watch this video before you try the last problem in WebAssign, because I think it'll clear up a lot of questions for you. Thank you.